Hello viewers, I am Dr. Mala Das Sharma and you are watching my channel Chemphilic. Let's start another episode of Teaching Chemistry through Riddles. I request you to see the video till the end so that you can enjoy the complete riddle. So let's start riddle number 16. I am a simple physical property of all the gases, which can be recorded by a thermometer. My value is fixed for each gas and I play an important role in liquefaction of gases by application of high pressure. You can write my expression by using van der Waals constants. So, this is riddle number 16. So, let's see the questions. The primary question is, who am I? Guess the answer. The answer is critical temperature. Now let's see the other questions. Number 2. How I am related to liquefaction of gases by application of high pressure. Number 3. What is my relation with van der Waals constants A and B? Number 4. What is the status of liquid and vapor phase of a substance when it attains my value? Now, this riddle is based on critical phenomena. So, we discussed this critical phenomena. See, gas can be liquefied either by decreasing the temperature or by increasing the pressure. Now, if you want to liquefy the gas by application of pressure, then above a certain temperature, the gas cannot be liquefied whatever pressure you applied. And this temperature is called critical temperature. And this is a characteristics property of each gas. Now, the pressure required to liquefy the gas at critical temperature is known as critical pressure. Now, what is critical volume? The volume occupied by 1 mole of the gas at critical temperature is called critical volume. So, this critical temperature, critical pressure, critical volume, which are denoted by Tc, Pc and Vc, are known as the critical constants of the gas. Now, at critical temperature and pressure, the physical properties of the gases are indistinguishable from the liquid form and no distinction can be observed between the two. So, at critical temperature, gaseous phase and liquid phase are indistinguishable. They have the similar characteristics. So, this phenomenon of smooth merging of the gas with its liquid form is known as the critical phenomena. Let's see with the diagram. Then it will be clear. Now, this Andrews experiments and the isotherm of carbon dioxide. Andrews did the experiment on carbon dioxide gas and we see the observation. Now, see, this is the curve for the Andrews experiment and this experiment is done at different temperature, different constant temperature, say 13 degrees centigrade, then 21 degrees centigrade, finally 31.1 degrees centigrade, then 35.5 like that. Okay. Now, we are considering this experimental observation at 13 degrees centigrade. Okay. Now, look at here. We start from here. If we start from here, the point A at 13 degrees centigrade temperature isotherm, temperature is kept constant 13 degrees centigrade. Okay. So, y-axis, along y-axis it is pressure, along x-axis it is volume. So, look at here, at the point A, the pressure is low. Pressure is low, obviously. Okay. And at this low pressure, it is entirely gas, which is represented by A. That means carbon dioxide is entirely in the gaseous form. Now see, on increasing the pressure, we are increasing the pressure slowly. Then if the pressure increases at constant temperature, then according to Boyle's law, volume decreases. Pressure inversely proportional to volume at constant temperature. So on increasing the pressure, see the volume is decreasing up to the point B according to Boyle's law. And it is shown by this isotherm portion, that is AB. Next, see, at this point B, the deviation from Boyle's law starts. And here you see B to C, the pressure is almost constant, but the volume decreases rapidly. That means the gas is converted to liquid. So at point C, coming to the point C, from B to C, there is a sharp decrease in the volume and the pressure almost same, and it is converted to liquid. So coming to the point C, at point C, the gas is completely converted to liquid. And then what is between B and C? Between B and C, the pressure remains constant and the gaseous phase and the liquid phase, they are in equilibrium. So it started from B when it was completely gas, then ends at C in this isotherm portion BC when it is completely liquid. Between B and C, there is a sharp change in volume, pressure remains constant, and at C, that means between B and C, it is converted to liquid, at C, it is completely liquid. Now, this pressure corresponding to this horizontal portion, this portion is known as the vapor pressure of the liquid at the temperature of this isotherm. Here we have taken the temperature 13 degrees centigrade. Now we'll see. This pressure volume curve, if we observe at 21 degrees centigrade, that means which is higher than 13 degrees, that means at higher temperature, see the nature of the curve is similar, almost same. But what are the exception? That liquefaction start at this B1, which is comparatively at higher pressure, and this horizontal portion, which is denoted here by B dash and C dash, it is comparatively shorter than that of the earlier one. These are the only exception. Otherwise, this nature of the curve is same. So this portion is shorter and this liquefaction start at B dash, which is at higher pressure compared to the earlier one. Now, again, if you increase the temperature, what we will find that this liquefaction will start at higher and higher pressure, and the horizontal portion will continuously decreasing. That means it will become smaller. And when the temperature will become 31.1 degrees centigrade, then this horizontal portion will become a point. So at this point, boundary between the two phases, what are the two phases? Liquid phase and the gaseous phase disappears, indicating that both the phase have identical characteristics. So at this critical temperature for carbon dioxide, it is 31.1 degrees centigrade. The boundary between the two phases disappears. Both the phases have similar characteristics. If we go above 31.1 degrees centigrade, so 31.1 degrees centigrade is the critical temperature of carbon dioxide. Now above this temperature, say it is 35.5. See, that is a continuous curve. You cannot differentiate that this is gaseous portion, then liquid and gas phase are in equilibrium, then liquid part, no. That means there is no liquefaction of the gas. And so above this critical temperature for carbon dioxide, it is 31.1 degree. There is no liquefaction of gas, whatever pressure you apply, no matter how much high pressure you apply, you will not liquefy the gas. So this isotherm at critical temperature is called critical isotherm. So at this temperature, that means 31.1 degrees centigrade, this isotherm of carbon dioxide is known as the critical isotherm. Left hand side of this green portion or green area, it indicates the liquid gas. Here it is liquid carbon dioxide, because we have seen that during this horizontal portion, gas is converted to liquid, and here liquid and gas are in equilibrium. Okay, so that just left hand side of this point C, or here C dash, this is the liquid gas, and here liquid carbon dioxide. Right hand side of this point B or B dash, this is the gaseous carbon dioxide, and this green area, already I told you, liquid and gas exist in equilibrium. Now let's see the other question. Question number 2. How am I related to liquefaction of gases by application of high pressure? Already you have seen the answer. Above critical temperature, gas cannot be liquefied by application of high pressure. If you want to liquefy the gas by application of pressure, you have to do it below critical temperature or maximum up to critical temperature. Above that, it is not possible. Third question. What is my relation with van der Waals constant A and B? A and B are the van der Waals constant. A is for pressure correction, B is for volume correction, and all these critical constants are related to van der Waals constant. So here, this critical temperature is equal to 8A divided by 27 RB. A and B are van der Waals constant, are universal gas constant. Number 4. What is the status of liquid and vapor phase of a substance when it attains my value? Already we have seen that at critical temperature, there is no boundary between liquid and vapor phase, and they are equally and indicating that both the phases have identical properties. You cannot distinguish them. So this was our riddle number 16. I'll be waiting for your valuable suggestions and comments.